Today we're going to look at a couple of interesting features on triangles known as the centers. And that is plural because there is actually more than one center to a triangle. It's depending on how you measure it. So we're only going to look at two of them today. There are four total. And these two that we're looking at are formed by the topics that we've been looking over recently. So let's talk about perpendicular bisectors first. First of all, a quick review on some theorems on the perpendicular bisectors. It says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So this point right here would be equidistant from the endpoints, and each of these line segments would be congruent as well, because point D is on the perpendicular bisector. And the converse of that is true also. So if a point is equidistant from the endpoints, so if E is equidistant from A as it is from B, then that means it would also be on the perpendicular bisector. Okay, a triangle has three sides, so it also has three perpendicular bisectors. Those would be the perpendicular bisectors of the sides of the triangle. The bisectors are congruent lines. And the point of concurrency of the perpendicular bisectors is called the circumcenter. So that's our first center of the triangle, circumcenter. And it is the point of intersection of the three perpendicular bisectors of a triangle. Okay, so our circumcenter theorem says the perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So this is my circumcenter. It is where the three perpendicular bisectors intersect, and the distance that this point is from each of the endpoints is congruent. So that means they already put a bunch of marks on here, but this would mean that PB, here we go, PB is equal to PA, which is equal to PC. So P to the vertex, P to this vertex, P to this vertex, those three line segments are congruent. Okay, and point P is the circumcenter of triangle ABC on this one over here, and they want us to list any segments that are congruent to each segment. So this would be a good place to pause the video and go back and read the theorem again, and then see if you can figure out the congruent segments to the ones that are given here, and then come back and check your work. Okay, welcome back. So line segment BR is congruent to line segment RA, line segment CS is congruent to line segment SA, and line segment BP is congruent to both line segment PA and also PC, since BP is one of the distances from a vertex to the circumcenter. Then that means each of the other distances to the vertices is also congruent. All right, so now we're going to look at the angle bisectors and the other center that we're looking at today, which is called the incenter. So the angle bisectors are the ray that bisects an angle, divides an angle into two congruent angles. So on this picture over here, for our angle ABC, if ray BD is the bisector, then that means angle ABD is congruent to angle DBC. The angle bisector theorem says that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So any point that's on this ray here would be equidistant. And when we measure that distance, we always measure it with the shortest path, which would be a line segment that's perpendicular to the sides of the angle there. So these two are congruent, according to this theorem. And the converse of that is also true. So if you've got the distance between each side of an angle is equidistant to a point that is on a ray within the angle, then that ray is the bisector. Okay, so similar to the perpendicular bisectors, since a triangle has three angles, it also has three angle bisectors. And the angle bisectors of a triangle are concurrent, which means they intersect at a single spot. Their point of concurrency is called the incenter. So the incenter is the point of intersection of your angle bisectors. So on my picture over here, I've got These three are angle bisectors shown by the arcs that are given. So their point of concurrency there is your in-center. Now what's different about this diagram from the last one, another of the differences, is that these line segments that are perpendicular to the sides, drawn from the in-center, are not a perpendicular bisector. So this point right here is not in the middle. Oh, that is awful. Oh, that's not going to let me do that. Okay, try it this way. Nope. Okay, I have to leave it. It won't go away. Ah, there we go. Okay, so point E is not the midpoint of line segment AC. That's what I was trying to say there. So this is not the midpoint, which means these two segments here are not congruent. Alrighty, so however, the angle bisectors of a triangle intersect at the point called the in-center, and that is equidistant from the sides of the triangle. So that would mean that these three line segments are congruent when you have the in-center. So PD, PE, and PF are all congruent. All right, so we have another guided practice problem here. Just get familiar with it together here. They tell me that point A is the in-center of triangle PQR. So this is my in-center, which means that each of the line segments that connect that to the angles is an angle bisector. And they also show me that this one here has a distance of 20. So pause the video here and see if you can answer these questions. All right, so on the first one, the angle measure there is 40 degrees because it is equivalent to the measure of angle ARK. On the second one, AU is equal to AT, and that measurement is 20. On the third one, the measure of angle QPA is equal to the measure of angle RPA because that is an angle bisector. And this were both given by algebraic expressions. So we can set those equal to each other and then solve. We get x is 11. But this did ask for the measure of angle QPA. So I took the expression for that one and substituted in the 11 for x. And I got 35 degrees. And for the fourth one, it's looking for the length of line segment QA. And with the information that we have on this picture, that actually cannot be determined.